Hi, thanks for coming here today. So today I'm going to talk to you about the future of Java. But first, the usual disclaimer sides. So a bit about myself. My name is Tobi. I'm a developer on the OpenJ9 virtual machine team. In the past, I've worked on VM support for Lambda expressions, so JSR 335. I've also worked on a multi-tenancy incubator project, where the goal was to run multiple Java applications on a single JVM instance. And I'm currently part of the Project Panama expert group. So the agenda for today, basically I'll start off by describing some of the challenges in Java today, more specifically with the JVM. And then I'll introduce Valhalla and Panama and show how these two projects solve some of these challenges. So in the last 10, 15 years, we're starting to see that the biggest challenge in CPU performance is memory latency. There are many cases where CPUs are able to process data faster than they can fetch it from memory. Modern CPUs tend to come with fairly large caches, about 8 megabytes on a consumer i7, and they can be as large as 120 megabytes on a PowerPC server chip. But the applications themselves are also getting larger. So being efficient with memory is still the key to good performance. So here's a simple architectural diagram. This is something you might find on an i7. Typically what happens nowadays is that CPUs are split up into nodes. They split into NUMA nodes. And the memory is split between the nodes. So for example, in this case, we have two NUMA nodes. So all the RAM is split between the two nodes. If a CPU in NUMA node 0 wants to access memory in NUMA node 1, it has to go through the inter-socket connection, which is a remote access. So each CPU has an L1 cache and a larger L2 cache, and a shared L3 cache for all the CPUs in the node. Here is a table showing some of the latency figures for accesses. So at the top is register access, which is basically a single cycle, so 0.3 nanoseconds. Below that is L1, which is about 4 cycles, and L2 at around 10 cycles, and L3, which is larger. You'll notice that between L3 cache and memory, there's a bit of a jump. It's over 5 times longer. And that's if it's on a local node. If you're accessing memory via the inter-socket connection layer, then it's even longer. And at the bottom is I/O, which is a few orders of magnitude longer. So basically, the purpose of this table is to show that it pays to condense your data. If you can fit all of the relevant data that you need into a small memory location, then you have faster accesses. So if you can put all the data that you'll access together in the same area, then you don't pay the latency cost as much. There are some things that GC policies can do to improve this situation. But for this talk, I'm only going to focus on Java data types and their layouts. So one of the great features of Java is identity. Identity lets you keep track of state. So a Java object has identity. This means that when its state mutates, it still remains the same object. So this is a very appealing feature, not just for Java, but for object-oriented languages in general. The issue is that there are some cases where you don't need the identity, yet you still have to pay the cost of identity. And as we'll see, the cost can be quite high. So in order to maintain the same view of an object, you need a reference so that everyone who's referring to it points to the same thing. So when you allocate an object, the memory allocator returns a reference to that object. And when the object's pushed on the stack, it's a reference that's pushed on the stack. If the object has non-primitive fields, then those fields are references. And for things like hash table, which have an array, then you have a bunch of elements that are pointed to by references. And those elements themselves can have more references. So eventually you end up with a complicated object graph with references everywhere. And it's easy to see how references can make up a large portion of our memory footprint. So one of the problems with references is that it involves a lot of pointer chasing. In order to access something, you need to dereference it. If you want to access a deeply nested field, then you have to dereference each of its containers. And depending on what the pointer is pointing to, this might be a relatively fast or slow access. So here's an example. We have the library object and the hash table object. Both are in L1, so the referencing books is fairly quick. However, the referencing table takes a little longer because it has to fetch it from L2. And the referencing the first entry in the table is even longer because it has to go to L3. You can create a similar example with NUMA nodes. In this case, hash table and library are in node 0. The entry array is in node 1, so you have to go through the inter-socket connection layer, which is more expensive than fetching from a local memory node. You can create a similar example with pages. As you saw in the table, fetching from disk is really slow. It's many orders of magnitude slower than memory or cache. So, for example, if you were on a virtualized environment and you overcommitted on memory, so you thought you had more memory than you really did, if you're in the situation where you have to fetch from I/O, then your performance will severely degrade. So this is why things like serialization is very expensive in Java, because you have to make a lot of dependent loads, which may cross many cache boundaries, require you to fetch memory from different nodes, and etc. Another great feature of Java is synchronization. This lets you have a consistent view of an object state in a parallel computing context. So synchronization is a very good tool. In order to support this mechanism, Java objects have a lock word. So an object header typically has class metadata, which describes its instance, and it has a lock word for cases like synchronization. The problem is in Java, every object can be locked. So every object needs a lock word, but you may not always end up locking the objects. So this is a bit of an overhead. So the reference and header overhead is very clearly seen with arrays. With object arrays, every element has a header and has a reference pointing to it. So basically, the overhead is 2 words multiplied by the number of elements. And if you have a small element, for example, if this was an array of javalang long, where the element is only a single word, then your overhead is about 200%. So the reference and header overhead contributes to loss of locality. Because you have more bloat, you're less likely to fit all the related data in the same cache line. And that's if your related data was allocated together in the first place. There are some GC policies that attempt to use profiling data to determine which fields are used around the same time to kind of improve locality, but there's no guarantee this will happen. One of the features of modern hardware is that they attempt to speculatively load cache lines that you will need. So when doing a sequential access, the hardware can load the cache line ahead of time so that the latency cost is hidden. So the way to make use of this right now in Java is using primitive arrays. If you're doing sequential access with a primitive array, then the CPU can preload the cache lines that you will need ahead of time. So this is shown to have advantages. If you're doing sequential access versus random access on a primitive array, you'll notice that the performance is much better with sequential access. With object arrays, however, this is not the case. In many cases, it actually looks more like this. There's no guarantee that your objects are allocated in order. So when you're walking an object array, you end up doing random accesses. So you get no help from the prefetchers. So in recent years, it's become more common for business applications to offload computing to a GPU. In order to do this, it requires the JVM to interop with native non-JVM heap data. So typically what would happen is you'd set your data up on the JVM heap, then copy it over to Off-heap, and then call a native library to send that data to your device. It's not just with GPUs, it's with things like RDMA. So there are some libraries that help out. OpenJDK provides a CUDA library, which are basically Java bindings that make this procedure seamless. But if the technology you're dealing with doesn't come with Java bindings, then there aren't many good solutions right now. The only real supported way to make native calls right now is with JNI. So JNI is a cool feature because it provides a standard way for the JVM to interop with native data. It provides native callbacks so that native data can call back into the JVM and access data that way as well. But some of the shortcomings of JNI is that it requires users to write JNI wrappers for every native function they want to call. This can be challenging because Java developers may not be comfortable writing C, or they may not want to write C. It can also be burdensome if you're dealing with a very large library. For every native function you want to call, you need a native wrapper. And then you have to build your wrapper library on every platform that you want to run it on. So to show you how difficult this is, we'll look at a small example. Here's some C code that uses a graphics library called Cairo. The code here is not so important. The important part is that we're making a lot of library calls. When you run this code, you end up with a picture. It's just a gray panel that prints hello world. So if we wanted to do the same thing with JNI, the first thing we do is we define all of the native functions that we want to call. So we basically write a function header for each of the native functions. In this case, we're fortunate because they're not hundreds. It's about 10. But still, this is a lot of work for a very small example. Also, you'll notice in the first case, we're using longs to represent native pointer types. And that's because there's no way to represent these types in Java. So this technique is called pointer stashing, where you basically hide a pointer in a long. The drawback to this approach is that you lose all type information. So it's easy to lead to bugs because you can confuse types. So here is the main function. As you can see, it looks very similar to the C main function. This part's not hard because it's all Java. The only drawback is that we are using longs to represent native types, so you have to be very careful with the naming to make sure you don't mix those up. So after you've written your Java code, you need to create your wrapper library. So you run java-h on your Java file, which generates a header file for all the native functions you need to implement. And here there are only 3, but there would be java-h will generate all of them for you. And then once you generate your headers, then you have to generate the implementation for them. In the first example, as you can see, what we're basically doing is taking the arguments from Java, passing it to our native function, getting the return, and passing it back. So we're doing the necessary conversions because on the Java side, we're representing everything as longs, but they have specific types. So we have to convert to the right type, and then on the return, we convert back to a long. In the second case, it's a little more involved because we're passing a Java string, so we have to convert this to the C string, then call the function, and return. So as you can see, this is a lot of boilerplate for doing something that's fairly simple. All we want to do is call a native function, but we've had to do all this extra work. And it doesn't scale quite well. If we were dealing with a big library, we'd have to do all this work over and over again. So there are some tools, there are some existing open source tools that make this situation a little better. There are tools like JNR and JNA, which generate Java bindings for native functions for you, so you don't have to do this yourself. However, they do have overheads. Internally, these libraries do use JNI to call out. So it's not going to be as fast as a direct C call. There's a lot of overhead in the transition. In order to do this quickly, in order to do this with good performance, you would need JVM help. Basically, you'd need a way for JITted code to directly call a C function without all the overhead. So another challenge is dealing with off-heap data. In this example, we have a structure which has an address and a port number. And this structure is located somewhere off-heap. So in order to interact with this data, you could use JNI. However, it would be very slow. The overhead would just be ridiculous in that case. So what most people do is they use unsafe. Unsafe lets you point directly to off-heap memory. But the main drawback is that you have to manage offsets yourself. So if you get things wrong, this can lead to crashes, which is not ideal. Another approach is using direct byte buffers. This is slightly better as you get bounce checks, but you still have the same problems with managing offsets yourself. There are also hardware capabilities like vector instructions in modern CPUs that, that help improve processing speed. So existing JIT compilers today do a pretty good job of loop unrolling and then using superroad optimizations to take a scalar operation and vectorize it. However, these optimizations tend to be very brittle and sensitive to code changes. So you're never really guaranteed that your code will be vectorized. So just to recap, some of the challenges today on the JVM are that there are too many references, arrays are out of line, the headers are large when you don't need block words. There is poor interop with native libraries. JNI is not really fun. Dealing with off-heap data is unsafe, and if you make it safe, it becomes slow. And there's no intrinsic support for SIMD. So around 2012, 2013, the J9 VM team released a feature called PackedObjects, which attempted to solve some of these problems. So basically, PackedObjects provided a way to describe data in its native format on-heap and off-heap. So what you do is you define a regular Java class that extended PackedObject, and you define its fields. And when you define a class, you're guaranteed that the fields are laid out in the order that they're defined and with the exact size. So in this case, we have class point, has two fields, x and y. So we're guaranteed that point is going to be only 8 bytes. With this particular example, if you created a Java object point, it'll probably only be 8 bytes because there's both of those fields are aligned. However, the point is that PackedObjects basically let you do what you can do with C structs. On the right is an identical example where we've defined a C struct with two fields with the attribute packed. So declaring a PackedObject is equivalent to that case. At the bottom, we have a class called line. This has two nested fields. So this class would be equivalent to declaring a struct line with two nested points. So the benefit of PackedObjects is that it has a very condensed footprint. So on the right is what you would normally get with regular Java objects. So you have references pointing to nested fields. But with PackedObjects, everything is inline. So you save two references and you increase locality. So reading a field with PackedObjects requires that the JVM generates a reference to that field. Since the data is part of is contained in an object, it's not extracted out, you just point to it. However, writing a field is not allowed because you may have multiple references point to the field. So if you overwrite the field, you may be overwriting other references, which is very different from the existing semantics with Java nested fields. So as a result, PackedObjects disallowed writing fields, but it did provide a way to do an explicit copy operation so that it was clear what you were doing. So some of the drawbacks of PackedObjects are that the drawbacks were caused because the goal was to allow Java users to create flattened types while providing all the features of regular Java objects. So things like identity, synchronization, volatility, etc. So one of the problems with identity is that you may have two references pointing to the same data, but they fail equality checks because the references are different. There's also issues with arrays. Arrays work very much like nested fields work. When you read an array, it generates a reference to that field. And you're not allowed to write an array because you might be changing everyone else's view of that array. So you can't use the existing Java array syntax as the semantics with PackedObjects is very different. Also, PackedObjects had a split hierarchy. So every packed object subclassed the packed object type, just like all reference objects subclassed Java object. So there's no way to convert between a packed type and a regular reference type. So this is a big problem because it's hard to interop with existing libraries. You can't convert between a packed byte array and a byte array, which is a very big challenge. So while packed objects got some of the things right, like improving locality, getting rid of references, making it easy to access off-heap data, it didn't quite work with the existing Java semantics. But it did drive the discussion to pushing for better on-heap memory layout and better interop with native data. And not long after, we got 2 new projects, Project Valhalla and Project Panama. So before I go further, I'll just add, these 2 projects are currently in progress, and there is no firm release date for when these things will be completed. So to start, I'll talk about Project Valhalla. The main features of Project Valhalla are var handles, value types, and generic specialization. So var handles is basically a better unsafe. It provides better atomics, better memory barriers, and it does it safely. var handles was actually released in Java 9. The focus right now is value types. These are basically immutable identityless types surfaced in the Java language. And after that will be generic specialization, which will allow you to create a list event that's actually backed by an int array rather than an object array. So in this talk, I'll mostly focus on value types and the progress that's been made to date. So the goal of value types is to add JVM support for immutable identityless types. Currently, the only way to specify immutability is with the final modifier. And this is only partly true because you can still write a final field. So existing JIT optimizations that try to treat a final field as constant will often install de-optimization points just in case the field changes. Being able to treat a field as constant is very important because it allows the JIT to disassemble types into registers or to stack allocate. Currently, if you want to do these things, you need to perform escape analysis, which determines whether a field will escape its method scope or if it can only be used by a single thread. So these things are expensive operations and are typically only done in higher compilation tiers, which means that you kind of have a performance cliff. You need to ramp up before you get to the optimal code. So value types are immutable. They're basically user-defined primitives. Hence the tagline, codes like a class, works like an int. So value types are immutable, and the JIT can trust this. So from a JIT optimization perspective, value types does make things a lot better because it makes it easier to get to high-performing code faster. And we'll see in the following slides that it has some other advantages as well. So as I said earlier, identity requires that you keep references to an object so that everyone has the same view of the object. But if you don't have identity, then the JVM is free to do away with references. The JVM can be express data types without pointer indirections. So it allows the JVM to flatten fields. Likewise with arrays, if you don't have identity, you can flatten the elements directly in the array. Since there's no identity, identity operations are disallowed. So things like wait, notify, synchronization, these things don't work. And since you can't do those operations, then you don't need the lock word anymore. So this also reduces the header size. So some of the goals of the value type feature are that it will also support encapsulation. So you can still define things like private fields. It will be able to interop with existing object types. So you can use it as instance fields, static fields, array elements with existing types. And one of the goals is that it should be able to interop with existing object types. So you can use it with existing Java code. So if we take a look at the JVM challenges, we see that Valhalla solves quite a few of these. It condenses the size, it allows packed arrays, and reduces the header overhead. So one of the early value type prototypes was minimal value types, MVT. The main goal of this prototype is to provide a minimal JVM implementation that people can experiment with. So there's no language support for this. Java-C doesn't help you create these. You have to use bytecode generators. But basically, MVT value types are data aggregates. So all instance fields are final. Comparisons for equality are done by state. They can never be null. And they don't support identity operations. They can't have a superclass, can't be subclassed, and you can't recursively define them. So a value type can't define a field of its own type directly or indirectly. So how does it work? First, you define a value-capable class. This is a regular Java class, except that it has a value-capable annotation. Also, the VCC has to be a final class, so it can't be subclassed, and it can't extend another class. All the fields you declare in the VCC also have to be final. However, you're allowed to define constructors and methods for behavior. So the VCC is compiled by Java-C, and the JVM creates a runtime representation of the class. So this part is not different than what you'd normally expect. However, the JVM can also generate a derived value class. So a derived value class is basically a copy of the VCC, except that it only has fields. So no methods, no constructors, no stack members. Also, it has an ACC value bit set in the class modifiers. So this lets the JVM know that it's a special type of class. DVCs have a separate hierarchy, so you can't cast from a DVC to a VCC. And since this is an experimental feature, it has the minor version set in the class file, so the JVM knows that it can use the special opcodes with it. Also, DVCs have Q signatures, which differentiates it from the existing L types. So here's basically the difference between a DVC and a VCC. On the right, we have VCC. So this is a regular Java object. So fields aren't nested in, you have references. But with a DVC, the JVM can nest everything. So you get a more compact format. Also, the signatures are different. So as I said, derived value classes are Q types, and value-capable classes are L types. So as I said earlier, there's no language support for derived value classes. They're never surfaced at the language level. In order to make use of it, you need to use bytecode generation tools like ASM or with MethodHandles. So MVT defines some new bytecodes. In order to create a value type, you use vDefault, which creates a new value type with default values. So basically a value type that's zeroed. vWithField takes an existing value type and updates a single field. Then there are operations like vload and vstore. These are basically identical toaload and astore, except that they work with value types. The same with vReturn. Then there are the array bytecodes, vAstore, and vAload, which read and write value types from an array. And then there's vbox. So vbox takes a value type and converts it into its value-capable equivalent. So this is how you convert between Q and L types. This is similar to converting between a long and a Java lang long. And then there are a few overloaded bytecodes. Things like getField need to detect whether they're referring to a value type or a reference type, so they know are you going to dereference a pointer to get the field, or is the field nested? Here's a table showing how to do this with MethodHandles. So MVT has a class called value type, and this type, you can query this class to get MethodHandles for the MVT opcodes. So you can query for a default value constant, which returns the method handle that creates a default MVT type, and you have some for vWithField, etc. So now we'll look at an example. So on the left are the bytecodes, in the center is the Java stack. So the first instruction is vDefault. It takes a class ref to a value type. So what this does, it works a lot like new. It creates a value type that's zeroed and then puts a reference on the stack. The next instruction is iLoad, and the third instruction is vWithField. So vWithField takes a field ref, which which points to the field that will be updated. vWithField will take an existing value type as well as the parameter for the field update and replace it with a new value type with the updated field, as we see here. So we can repeat this again for the Y field, and now we have set up our value type. So the key takeaway here is that vWithField doesn't update a value type, it creates a new type with an updated field. You can't update a value type since they're immutable, just like you can't change an int literal 1 to an int literal 2. 1 is always 1, 2 is always 2. In order to call a function with value types, you need to convert the DVC to a VCC. So as I said earlier, DVCs don't have any methods. So in order to convert between a DVC and a VCC, you use the VBox operation. So the VBox bytecode points to the class ref of the VCC. So it takes an existing value type on the stack and replaces it with a value-capable class. So a value-capable type is just a regular Java type, so you can use things like invoke virtual with it. So some of the drawbacks with MVT, the most obvious one is it's hard to program with. Bytecode spinning is not natural to most Java programmers. Also, you get no static type checking. And method handles is not that much easier. Even basic operations with method handle combinators can be very complicated. But this is not really a big deal, as MVT is an experimental feature. It was just a quick way to get the val type feature out there so people can play around with it. One of the more serious drawbacks is that interoping between Q and L types are kind of difficult. As we saw earlier, if we wanted to call a method, we had to use the VBox operation to convert with a Java type. So this has surprising behavior, as you are creating identity at the point of conversion, and you remove it when you unbox. So this can lead to bugs, as people may expect that something has identity when it really doesn't. Another issue is that migration of old code requires that you generate a lot of method bridges. So if you define a method with a Q type, existing code doesn't know anything about it. So you need to provide a method bridge that does the necessary conversion to the Q type. So this increases the overhead. So MVT was an early prototype. LWorld is basically the next step. The basic idea is that today's L types, today's references, these are considered legacy L types, and then the value types are Q types. So in LWorld, the legacy L types and Q types are both treated as L types. So everything's an L type in LWorld, hence LWorld. So this is currently a work in progress. Anything I say about this may change, as this is under active development. But I'll just give you a brief discussion on which direction this proposal is going. So the basic idea is you have 4 reference types. You have object types, so these are the legacy L types. You have value types, array types, and interface types. And all of these are L types. So the value types are distinguished by an ACC value bit on the class modifiers. So this is similar to the ACC value bit in MVT. So when this bit is set, it means that the particular reference has no identity, and all the fields are implicitly final. So you can't use a put field operation to update them. These types can have methods. However, they have no non-private constructors, so you need factory methods to instantiate them. Also, because these types are L types, they have a shared hierarchy with Java-lang object. So you don't need things like boxing. Everything's an L type, so it interrupts nicely. There's also an ACC flattenable field modifier bit that you can set on a field. What this means is that the field may be flattened. It doesn't guarantee that it will be flattened, but it allows the JVM to flatten the field. It also means that the field can never be null, so you can't assign null to that field. And you can't recursively define that field. So the container that sets this flag cannot set it on a field of the same type, either directly or indirectly. It's a similar restriction with MVT. Currently, anytime this bit is set, the field has to be a valid type, but that may change in the future. And arrays are implicitly flattenable. So in LWorld, flattenability is a property of the field, not the type. So LWorld borrows only 2 bytecodes from MVT. vDefault becomes default value, and vWithField becomes withField. The rest of the bytecodes, things like AStore, ALoad, AAStore, ALoad, AReturn, those bytecodes are overloaded. So they detect the type that they're referring to. If it's a valid type or a reference type, to determine their behavior. So one of the big challenges with the LWorld approach is nullability. As I said, you can never write null to a value type. So if you create a valid type array, you can't assign null to it. However, because in LWorld, valid types share the same, have the same hierarchy as reference types, you can cast a valid type array to an object array, and then in that case, you can write null. So this is one of the big problems with this approach, and it's one that the expert group is actively working on, and hopefully there'll be a solution soon. So for the remainder of the talk, I'll talk to you about Project Panama. So the big goal of Panama is to basically improve native interop between the JVM and native data. So some of the features are that it will let you describe native types. So earlier we saw that in order to describe native pointers, we use longs. With Project Panama, you'll be able to do this with, proper type safety. It'll also provide better FFI, so basically JNI 2.0. The goal is that it won't require developers to write JNI wrappers for every native function they want to call. They'll be able to call native libraries directly. And it will also allow you to interact with off-heap data directly. So instead of using unsafe and managing offsets manually, the runtime will generate types that do this for you. Panama will also provide a vector intrinsic API. So this lets you define SIMD instructions in your code with the confidence that the compiler can actually optimize it down to the correct instructions. So to summarize, Panama lets you do everything you're currently doing and more in a better and safer manner. So if we take a look at the challenges, we can see that between Valhalla and Panama, they're all basically solved. Panama improves interop with native libraries. It makes it easy to interop with off-heap data, and it will add support for SIMD instructions. So this is a basic overview of the layout and FFI part of Panama. I'll talk about the SIMD stuff later. So basic idea is you begin with your native structure definitions. So these are things like C header and source files. You feed that into a native data extraction tool. So this tool basically extracts the name of all the structs, the name of all the fields, their sizes, their offsets, all the methods that you've declared, the arguments, return types, etc. So it extracts all this data and then generates interfaces with getters and setters and abstract methods that represent the native functions. It also emits a layout description. The layout description describes the exact size of fields, the exact offsets, etc. So basically, you use these interfaces in your code to do the operations that you want to do, like assigning fields to off-heap data or calling methods. So once you've written your code, you start your application. The runtime library will generate implementation classes for these interfaces. And so it will generate implementations for all the getters and setters with the exact offsets for the fields. The runtime API also includes helpers for transforming between Java and C types. So it has helpers for things like converting a Java string to a C string. So I'll do a quick example. Here we've defined two structs, points and line. And you can also define functions as well. So over here, I've just put the headers, but they could have been function bodies as well. So you'll see here that we can define things with pointer types. So the first function returns a pointer to point. You can do this with JNI, but as I said, you have to use techniques such as pointer stashing. In the second example, we're returning a points by value. So to do this with JNI would be very difficult. You would have to basically deconstruct the return type and then either use JNI callbacks to assign the fields directly or use unsafe to copy the data over. So this is one of the benefits of Panama. It has a much wider range of function calls that it can do. Likewise, with the third example, we're calling a function passing structs by value, which would be very difficult with something like JNI. So the next step, once you've got all your native structures, you feed that into a tool called JExtract. So this is the tool that extracts the native data from your native data files. And JExtract takes all your native files and produces a jar with interfaces. So using the JExtract is very simple. Sample commands at the bottom. So the -t, that basically says which package you're going to put all your interfaces in. The -o says where all the interfaces will be generated, and the last argument is your source file. So here's a table with the type mappings. The mappings between primitive types seems fairly straightforward, but for things for C types, there are signed types and unsigned types, which you don't really have in Java. In Java, everything is signed, so there is a bit of a mismatch there. Also, C types tend to have a range. So long can be a 32-bit value or a 64-bit value, depending on the platform. However, in Java, long is always 64 bits. So this is why we need something like the layout descriptor, which lets you know exactly how big these types are. For things like structs, they're represented with interfaces, and there's a pointer type, which represent pointers. The type parameter represents the thing that you're pointing with. So going back to our example, the generated interfaces look something like this. JExtract would generate like an enclosing interface for the entire library. Each structure that is declared in your source file is an interface. So as you can see, there's an interface with point. So it has getters and setters, the $$ get for the getter, and the setter below it. It also has a helper to get a reference to the type. So this is like the ampersand operator in C. So there are some annotations on the points interface. The @C annotation is basically for debugging, so it tells you where you got your structure from, what line number, etc. The native layout one is more interesting. It basically tells you the layout of the structure. So points is 2 integers, so we have the brackets represent a structure, and the 2 y's are the fields. And then there's a mapping between the Java type and the C type. So the Java type is an interface point, but the C type is a struct point. Also, we have the size of points. So as I said, primitive types may vary depending on platform, but with the type description here, we always know the exact size of the structure. If you look at the abstract methods, you'll see that there are also annotations there. So they're very similar to the ones on the interface. There's a native layout annotation which describes the field. There's also information that describes the size of the field. So we know the type in the specific platform. Also, there is the offset information. So this is used by the layout runtime to generate the implementation classes, which will hard code the offsets so that when you use the getters, you can fetch directly from that offset. And so each field gets the getters and setters. I haven't showed why, but it's basically identical. The only difference is that the offset will be at 4 instead of 0. So here's another example with line. As we can see, we have getters and setters for the nested point field. So now we'll look at the functions. So the functions are very similar. They have an annotation for debugging information, but they also have a native type annotation, which describes the arguments as well as the return type. So in the first case, the arguments are 2 integers, so that's in the brackets, and the return type is a pointer to a point struct. So the P means pointer, and then the colon, and the thing following the colon is the return type. And likewise for the rest of them. The calling convention annotation basically describes how to make the call. So in this case, the 1 represents a standard C system V calling convention. So the great thing about Panama is that all the stuff is generated for you. So working with a large library is as simple as working a small one. You don't have to handwrite any wrappers. It's all there. So when you want to write the code, first you use the native library helpers to load the library, and then you bind the native library to your Panama to the generated interface. So this operation basically does DLSIM for each function defined in the interface. So it finds the exact address of each of the functions, and then it creates a native method handle that points to those functions and assigns them. And these native method handles are called in the concrete implementation of the abstract functions. So calling a native method with Panama is very simple. As you can see, it's literally just a Java call. So there's no need for JNI wrappers, no need for declaring native method stubs. You just simply call a Java method. So here is what one of the methods are doing. So getPoint malloc some memory, assigns the fields, and then returns a point. So as you can see, using Panama makes it very easy to interop with off-heap data. We're here writing Java code, and we're pointing to data that's off-heap without using unsafe. So this is a very cool feature. The Panama runtime also provides API to convert between Java types and C types. So converting between a Java string and a C string is very easy. There's also a thing, you'll notice the last argument is a scope. So this is a native scope. The conversion here allocates some memory to store the C string. So Panama provides things like scopes which manage all your memory allocations. So you can use scope try with resources blocks. So basically, as soon as you exit the scope, everything is deallocated. And if you try to access something that's out of scope, you get an exception. So it just makes it easier to deal with memory management. So now I'll quickly talk about the vector API. So the vector API is basically a library with vector operations that the JVM recognizes. So the JVM attempts to optimize these operations down to the individual SIMD instructions. So here's a quick example. We have a float species instance. This lets us fetch data from an array with vector load, as you can see with the species from array. So this fetches data and places it in a vector. And when we have the vectors, we can then perform vector operations. So as I said, the JVM recognizes all these functions. The JIT tries really hard to basically provide the equivalent machine code instructions for each of these. So to quickly recap, some of the biggest challenges in the JVM are that there are too many references, arrays are not ideal, the headers are large when you don't need locking, interop is hard, dealing with off-heap data is hard, and there's no intrinsic support for SIMD. But with Valhalla and Panama, we have solutions to all these challenges. So I think I'm out of time, but thanks for coming to my talk. If you have any questions, I can take them either now or on the side. If if you have any questions about the presentation or just JVM stuff in general. Yeah.
Hello. Oh, good. Sorry. I wasn't able to fully understand the difference between the pointer to something.
Yeah.
And later in the slides appeared reference to something. So I wasn't really.
Okay, sure.
I didn't really get that because the reference is like an ampersand. I get that. Pointer is like a pointer, but in C they're all the same. So.
Yeah. So basically, these are when JExtract generates an interface for a structure, it generates all the accesses that you might want to do with a field. So the common ones are writing a field or reading a field. But in C, you can also return a reference to a field. So that's what the reference thing does. It's basically, here's something, but give me something that points to it. So in many ways, reference and pointer are very similar. But languages like C do make a distinction between the pointer type and the ampersand. So the layout, the generated helpers also make the same distinction, if that answers your question.
I mean, I've coded in C a lot. I don't remember the difference between...
Talking about C++ might be. When you say difference between reference and pointer, you're talking about C++ rather than C.
No, I'm actually talking about C.
Okay.
I'm talking about, this is equivalent to prefixing an ampersand and then the struct and then the field. So that's basically what that thing will do.
Okay. Yeah. I didn't know that was put in C as well. Okay, cool. I thought it was only C++.
Oh, no, this is not for, this is not something that you'd put in a function header. This is something that you would do if you wanted to get a reference to a field.
No, I got that. Thank you.
Yes.